How does the potential difference across different branches in a parallel circuit compare with one another? We're going to build these 3 circuits. Notice that in each we have one battery. You might call it one cell in each circuit. In the first circuit, we just have one resistor in series with that cell, and we're going to measure the potential difference across it. That one resistor is going to have a resistance of 10 ohms. In the second and third circuits, we also have a 10 ohm resistor. But the difference is, in these 2 circuits, that 10 ohm resistor is in parallel with at least one other resistor. In the middle circuit, there are 2 resistors in parallel, the 10 ohm and a 20 ohm resistor. And we measure the voltage across that parallel branch. And then we're also going to measure individually just across the 10 ohm and just across the 20 ohm and across both of them in parallel. In the third circuit, that 10 ohm resistor is in parallel with 2 other branches, each of them being 20 ohms. So we have 3 parallel branches there. And again, we're going to measure the potential difference across each of those branches and across the circuit as a whole. Notice in each circuit, we don't have any resistors in the main part of the circuit. We don't have any resistors besides the ones that I've been speaking about now. If there were, then the circuit would be a little more complex than what we're going to discuss in this movie. So let's now open our simulation and build these circuits. We put one cell into each of the circuits. We have a 10 ohm resistor in each of the circuits. In the first circuit, that's all we have. So let's connect all of that with wires. In the second circuit, that 10 ohm resistor is in parallel with a 20 ohm resistor. So we use connecting wires in such a way that there are branches in the circuit. Then we close the main part of the circuit as well. So there we have circuit 2 complete. Circuit 2 has 2 resistors in parallel with one another. Notice this resistor is 10 ohms, this resistor is 20 ohms. In the third circuit, we have 3 branches. The first one is of 10 ohms, the second 20 ohms, and the third one also 20 ohms. We connect the wires in such a way that the circuit branches, and it branches 3 ways. We also close the circuit in the main part of the circuit using wires. Now, since there's no bulb, we can't by eye see what's happening here. But what we are going to do is we're going to bring in a voltmeter, and we are going to measure the potential difference, the voltage, across each of these resistors, as well as across the circuit as a whole, in other words, across the batteries. But before we do that, let's discuss what is our focus question. In this case, we have 2 independent variables. There are 2 things that we are making different between our measurements. So one of them is different between the 3 circuits. So there we can see each circuit as a treatment. What is different between the 3 circuits? That is the first independent variable that we're looking at. But then, between each measurement, even within a circuit, there is something that is going to be different. Because we are trying to do 2 investigations within one, just to save time here. So what is the second independent variable that we are looking at while we're at it? And then what are we going to measure? What is our dependent variable? How does number of parallel branches and their resistances affect the potential difference across them? So it's easy to see that number of parallel branches is one of our independent variables because our 3 circuits differ in the number of parallel branches. Here we have, well, actually no parallel branches. Here we have 2 parallel branches, here we have 3. But then each time we take a measurement, that is also, we could say, a treatment. And if you look, for example, in this third circuit, we are going to measure the potential difference across this 10 ohm resistor and then across this 20 ohm resistor. And they don't have the same resistance as one another. So we are also looking at the resistances of the parallel branches and wondering, is that going to make any difference? How is the potential difference across this resistor going to compare to the potential difference across this resistor? So those are our 2 independent variables, the number of parallel branches and the resistance of each of the branches. And then our dependent variable is what we're going to measure it's the outcome. And the thing that we're going to measure is the potential difference across the branches. What must be the same between the three circuits to make this a fair test? We're going to use the same potential difference across the battery. So we're going to use, in this case, a 9-volt battery in each of the three circuits. So what is your prediction? What do you think we are going to find? What is the answer to this question? Do you think that we're going to get the same reading here as here as here? Or maybe different readings? If so, is it going to maybe be a higher voltage here or maybe a higher voltage here? And then across the different branches, what are we going to find? Do you think that we'll find the same voltage across the 10 ohm as the 20 ohm here, or different voltages? If different, which one will be higher? And how will the voltage across this 20 ohm compare to this 20 ohm? And how will the voltage across this 20 ohm compare to that 20 ohm? And how will the voltage across each of the 10 ohms compare? Why do you say what you say? Let's prepare a table for our data. Remember, we have two independent variables in this case. So when we say the heading, table showing the relationship between, we have two things which are our independent variable. What are they? And in our table, we also need two columns for the independent variables. What are they, and do they have units? We only have one outcome, one dependent variable, the potential difference across them meaning across the branches. So where does it go into the heading? And we know that it belongs in the last column. What is its unit? Table showing the relationship between number of parallel branches and their resistances. Those are our two independent variables. So number of parallel branches goes in the first column of our table. That does not have a unit, but resistances, which we could say resistance of branch. When we say their resistances, we mean the resistance of each of the branches. That does have a unit, ohms. We have one dependent variable, the potential difference across them. In other words, the potential difference across each branch. We shorten that in the table simply to potential difference. We could even call it voltage. Potential difference and voltage mean the same thing here, and the unit of potential difference is volts. Notice how I've structured the table. There are three different numbers of parallel branches we're going to use. So three treatments regarding that independent variable. So there are three places to put in information there. What information should go in those gaps? But for the resistance of the branches, there are not just three treatments. What goes in those gaps? Our first circuit has one parallel branch. Actually, it doesn't have any parallel branches. It's just one series circuit. The second circuit has two parallel branches and the third three parallel branches. In the first circuit, there's only one resistor with resistance 10 ohms. In the second circuit, we have two branches. One branch has resistance 10 ohms and the other 20 ohms. And in the third circuit, we have three branches. One has a resistance of 10 ohms and the other two each of 20 ohms. So now we have our table ready. We're ready to go and take our measurements so that we can put this information into the table. Have you predicted what are we going to find? So we go back to our simulation, we take out our voltmeter. Let's go to the first circuit. The potential difference across the battery is 9 volt. The potential difference across the 10 ohm resistor is also 9 volt. This is not surprising because remember that the voltage that the battery puts in this case 9 volt, must be taken out by, in this case there's only one resistor, by that one resistor. So 9 volt is taken out by the 10 ohm resistor. Let's go to the second circuit. We measure the potential difference across the battery. Unsurprisingly, it's 9 volt. What are we going to find when we measure the potential difference across each of the resistors? Across the 10 ohm resistor, 9 volt. Across the 20 ohm resistor, 9 volt. We measure across the whole parallel section, 9 volt. Is that what you predicted? Let's go to the third circuit. What do you think we're going to find there? Across the battery, 9 volt. That's not surprising because we know it's a 9 volt battery we put there. Across the 10 ohm resistor, 9 volt. Across the 20 ohm resistor, 9 volt. And the other 20 ohm resistor, also 9 volt. We can measure across the whole parallel section, 9 volt. We put all that in our table. So what do you see? What is the answer to this question? How does number of parallel branches and their resistances affect the potential difference across them? I hope that you can see our conclusion is that in an ideal circuit, now notice we have been working with a simulation which is ideal. There's no battery internal resistance. If you actually do this in the lab, you will not have a perfect and ideal circuit. And so the experimental error that you get there might stop you from seeing this conclusion. Later you will learn about battery internal resistance, which is causing this experimental error. If you could have perfect batteries like in my simulation, or very, very fresh ones, then you would find this conclusion. In an ideal circuit, the potential difference is the same across all the branches which are in parallel with one another, regardless of the number of branches and regardless of their resistance. Regardless means it doesn't matter what the number of branches is. It makes no difference how many branches you have and what the resistance is. All of those branches that are in parallel with one another have the same potential difference across them. How do we understand this? Let's go back to this analogy. Remember that in this analogy, each blue circle stands for a coulomb of moving charge. Each red line stands for a joule of electrical energy. And voltage, or potential at a point, means how many joules each coulomb has. How many red stripes inside one blue circle at a point. That is what potential means. So the potential at this point is 9 volt, meaning that every coulomb has 9 joules of energy. Why does every coulomb have 9 joules of energy here? Because these coulombs have just come out of the battery, and that particular battery gave each coulomb 9 joules of energy as they move through the battery. Now, where can those joules of energy be lost out of the circuit? They can only exit the circuit as the coulombs move through a resistor. So here we have good conductors all the way between the positive terminal and the start, we could say, of a resistor. So all these coulombs in this section here have not yet gone through a resistor. So they have not yet had any of their energy taken out of them. So they all still have 9 joules per coulomb. They all still have a potential of 9 volt. They are all at the same potential. All points joined by good conductors are at the same potential, because a good conductor cannot take away the energy from the coulombs. So a good conductor cannot change the potential of the charges. So all of these points are at 9 volt potential. Now if you look at the path that each coulomb can go along here, coulombs either can go along this circuit. A circuit means circle, from one point round and back to that point. So we could say from the positive terminal round and back to the positive terminal. So either the charges can go through this circuit or the charges can go through that circuit. A single charge can't do both at the same time. They have to choose this way or that way. And whichever one they choose, there is only one resistor in that path. If they choose this path, it's a 2K resistor. If they choose that path, it's a 1K resistor. Each coulomb will go through only one resistor. But they have to come back to the negative terminal on the path that they take with 0 joules of energy. That is a rule about electricity. That's how electricity works. And since each path only has one resistor along the path, well then, they have to lose all 9 joules per coulomb. They have to lose all 9 volts through the one resistor that they go. And that's what you see here. These coulombs go through that one resistor, losing all 9 volts as they do so, coming out with 0 volts. And these coulombs that go through that resistor lose all 9 volts as they do so, coming out with none, with 0. So all these points over here are at the same potential as one another, 0 volt. So you can see, if we were to measure the potential difference across each of these resistors, what that means is we feel with our voltmeter how many joules per coulomb here and compare it to how many joules per coulomb here, and we get the difference. Here it's 9 joules per coulomb, 9 volt, and here it's 0 joules per coulomb, 0 volt. 9 minus 0 equals 9 volt. So the voltmeter tells us 9 volt. What about across here? The voltmeter feels 9 volt here, 9 joules per coulomb here. The voltmeter feels 0 volts here. It tells us the difference, 9 minus 0, 9. We get the same reading across each of the branches. V in equals V out. And in a simple parallel circuit like this, where there is no resistor in the main part of the circuit, that also equals the voltage across branch 1, which also equals the voltage across branch 2.